Welcome back to The Chill Scientist. Every object around us is made of something. The chair you sit on, the phone in your hand, the walls of a house, the road beneath your feet, even the clothes you wear. All of these things are built from materials. Some materials come directly from nature, like wood, stone, or cotton. Others are created by humans through science and engineering, like steel, glass, plastic, or silicon. When we look at the history of human civilization, we can often understand it simply by asking a basic question. What materials were people able to use at that time? Long before modern science explained how materials work, humans were already learning through experience which substances were useful and which were not. Early humans discovered that certain stones could be sharpened to make cutting tools. They found that wood could be shaped into handles or burned to produce heat. Clay could be molded when wet and hardened in fire to make containers. Over thousands of years, people slowly learned how to shape, combine, and improve the materials around them. In fact, historians often divide large parts of human history based on the materials people used for tools and technology. The earliest period is known as the Stone Age, when most tools were made from carefully shaped rocks. Later came the Bronze Age, when people learned how to melt and mix metals to create stronger tools and weapons. After that came the Iron Age, when an even stronger metal allowed for more durable tools, better farming equipment, and more powerful societies. These names, Stone Age, Bronze Age, Iron Age, show how closely human progress is tied to materials. Each time humans discovered a new material or a new way to shape one, it changed what people could build, grow, travel, or protect. Materials shape almost everything about the world we live in. The houses people build depend on the strength of the materials available. Transportation systems rely on materials that can withstand stress, heat, and long use. Even communication technologies, from printed books to smartphones, depend on special materials that can carry information or conduct electricity. A bridge, for example, requires materials that are strong enough to hold enormous weight without breaking. Glass used in windows must allow light through while still protecting people from wind and weather. The metals used in airplanes must be both strong and lightweight so the aircraft can fly safely. In modern electronics, tiny materials inside computer chips control the flow of electricity and make digital technology possible. For most of human history, people discovered useful materials by trial and error. A rock that could be sharpened became a knife. A metal that could be hammered into shape became a tool. A substance that melted when heated could be poured into molds and shaped into new forms. But as science developed, humans began to understand why materials behave the way they do. Scientists discovered that all materials, whether stone, metal, wood, or plastic, are made from incredibly small building blocks called atoms. These atoms combine in different ways to form substances with very different properties. Some materials are hard and strong because their atoms are arranged in tight, rigid structures. Others are soft or flexible because their atoms can move more freely. Some materials conduct electricity easily, while others block it. These differences come from the tiny structures inside the material, structures too small to see with the naked eye. Understanding these hidden structures allowed scientists and engineers to begin designing new materials instead of simply discovering them in nature. This ability changed the world. Modern materials such as stainless steel, advanced plastics, carbon fiber, and semiconductor crystals were not found lying around in nature. They were carefully developed through experiments and research. Today, materials science is one of the most important fields in engineering and technology. Every new invention, from electric cars to space exploration, depends on materials that can handle extreme conditions. Rockets must survive intense heat. Batteries must store large amounts of energy safely. Computer chips must control tiny electrical signals with incredible precision. Even though the technology has become more complex, the basic idea remains the same as it was thousands of years ago. Humans look at the materials available to them and ask, what can we build with this? In many ways, the story of civilization is really the story of materials. Each new discovery gives people new possibilities. Stone tools allowed early humans to hunt and prepare food more efficiently. Metal tools allowed farmers to work the land more effectively. Steel allowed engineers to build railroads, bridges, and skyscrapers. Modern electronic materials allow computers and communication networks to connect the world, and the story is still continuing. Scientists today are developing materials that can heal themselves when damaged, materials that are stronger than steel but lighter than aluminum, and materials so small they must be studied with powerful microscopes. To understand how all of this became possible, we first need to look deeper into what materials are actually made of. Even though they feel solid and permanent to us, every material is built from tiny pieces far too small to see. These building blocks form the hidden structure that determines how every material behaves. Every object around us is made of something: the chair you sit on, the phone in your hand, the walls of a house, the road beneath your feet, even the clothes you wear. All of these things are built from materials. Some materials come directly from nature, like wood, stone, or cotton. Others are created by humans through science and engineering, like steel, glass, plastic, or silicon. When we look at the history of human civilization, we can often understand it simply by asking a basic question: what materials were people able to use at that time? Long before modern science explained how materials work, humans were already learning through experience which substances were useful and which were not. Early humans discovered that certain stones could be sharpened to make cutting tools. They found that wood could be shaped into handles or burned to produce heat. Clay could be molded when wet and hardened in fire to make containers. Over thousands of years, people slowly learned how to shape, combine, and improve the materials around them. In fact, historians often divide large parts of human history based on the materials people used for tools and technology. The earliest period is known as the Stone Age, when most tools were made from carefully shaped rocks. Later came the Bronze Age, when people learned how to melt and mix metals to create stronger tools and weapons. After that came the Iron Age, when an even stronger metal allowed for more durable tools, better farming equipment, and more powerful societies. These names, Stone Age, Bronze Age, Iron Age, show how closely human progress is tied to materials. Each time humans discovered a new material or a new way to shape one, it changed what people could build, grow, travel, or protect. Materials shape almost everything about the world we live in. The houses people build depend on the strength of the materials available. Transportation systems rely on materials that can withstand stress, heat, and long use. Even communication technologies, from printed books to smartphones, depend on special materials that can carry information or conduct electricity. A bridge, for example, requires materials that are strong enough to hold enormous weight without breaking. Glass used in windows must allow light through while still protecting people from wind and weather. The metals used in airplanes must be both strong and lightweight so the aircraft can fly safely. In modern electronics, tiny materials inside computer chips control the flow of electricity and make digital technology possible. For most of human history, people discovered useful materials by trial and error. A rock that could be sharpened became a knife. A metal that could be hammered into shape became a tool. A substance that melted when heated could be poured into molds and shaped into new forms. But as science developed, humans began to understand why materials behave the way they do. Scientists discovered that all materials, whether stone, metal, wood, or plastic, are made from incredibly small building blocks called atoms. These atoms combine in different ways to form substances with very different properties. Some materials are hard and strong because their atoms are arranged in tight, rigid structures. Others are soft or flexible because their atoms can move more freely. Some materials conduct electricity easily, while others block it. These differences come from the tiny structures inside the material, structures too small to see with the naked eye. Understanding these hidden structures allowed scientists and engineers to begin designing new materials instead of simply discovering them in nature. This ability changed the world. Modern materials such as stainless steel, advanced plastics, carbon fiber, and semiconductor crystals were not found lying around in nature. They were carefully developed through experiments and research. Today, materials science is one of the most important fields in engineering and technology. Every new invention, from electric cars to space exploration, depends on materials that can handle extreme conditions. Rockets must survive intense heat. Batteries must store large amounts of energy safely. Computer chips must control tiny electrical signals with incredible precision. Even though the technology has become more complex, the basic idea remains the same as it was thousands of years ago. Humans look at the materials available to them and ask, what can we build with this? In many ways, the story of civilization is really the story of materials. Each new discovery gives people new possibilities. Stone tools allowed early humans to hunt and prepare food more efficiently. Metal tools allowed farmers to work the land more effectively. Steel allowed engineers to build railroads, bridges, and skyscrapers. Modern electronic materials allow computers and communication networks to connect the world. And the story is still continuing. Scientists today are developing materials that can heal themselves when damaged, materials that are stronger than steel but lighter than aluminum, and materials so small they must be studied with powerful microscopes. To understand how all of this became possible, we first need to look deeper into what materials are actually made of. Even though they feel solid and permanent to us, every material is built from tiny pieces far too small to see. These building blocks form the hidden structure that determines how every material behaves. If we could shrink ourselves down smaller and smaller, far beyond what even the most powerful microscope can see, we would eventually reach the tiny building blocks that make up every material in the universe. These building blocks are called atoms. Everything around us, stone, metal, water, air, wood, glass, and even our own bodies, is made from atoms arranged in different ways. Atoms are incredibly small. A single grain of sand contains trillions upon trillions of them. Because they are so tiny, people did not discover their existence until fairly recently in human history. For thousands of years, philosophers and scientists tried to understand what materials were made of, but they could only guess. Some ancient thinkers believed that everything was made from basic elements like earth, water, air, and fire. The modern understanding of atoms began developing during the 19th century, when scientists studying chemistry started noticing patterns in how different substances reacted with each other. They realized that materials seemed to combine in very specific proportions, as if they were made of small pieces that joined together in predictable ways. This led scientists to propose that all matter was built from tiny units, atoms, that could connect to form larger structures. Although atoms are far too small to see directly with the naked eye, scientists have developed instruments that allow them to study how atoms behave and how they are arranged inside materials. Through these studies, scientists discovered that different kinds of atoms exist. These are known as chemical elements. Iron, oxygen, carbon, copper, and gold are all examples of elements, each made from a different kind of atom. What makes materials so varied is the way atoms combine and arrange themselves. Some materials contain atoms that pack together very tightly in strong patterns. These materials tend to be hard and strong. Others contain atoms that are arranged more loosely or in chains that can bend and move, which makes the material flexible. Take diamond and graphite, for example. Both are made entirely from the same type of atom, carbon. Yet diamond is one of the hardest materials known, while graphite, the material used in pencil leads, is soft and can easily leave marks on paper. The difference comes from how the carbon atoms are arranged. In diamond, the atoms form a strong three-dimensional network that holds everything tightly together. In graphite, the atoms form flat layers that can slide over one another, making the material soft. This shows that the properties of a material, whether it is hard, soft, flexible, or brittle, depend not only on what atoms it contains, but also on how those atoms are organized. Metals provide another good example of how atomic structure affects material behavior. In many metals, atoms are arranged in regular patterns that allow electrons to move freely through the material. This is why metals conduct electricity and heat so well. It is also why metals can often be bent or shaped without breaking, because the atomic layers can slide slightly while still remaining connected. Other materials, such as glass or ceramics, have atomic structures that are more rigid. These materials can be very strong, but they are often brittle, meaning they can crack or shatter if too much force is applied. When glass breaks, it happens because the atomic bonds inside the material cannot shift easily to absorb stress. Scientists and engineers study these atomic arrangements to understand how materials behave under different conditions. By changing the way atoms are arranged, by heating, cooling, mixing, or adding other elements, engineers can create materials with improved strength, flexibility, or durability. For example, steel is made by adding a small amount of carbon to iron. This small change alters the atomic structure of the metal, making it much stronger than pure iron. This simple discovery allowed humans to create tools, buildings, and machines that could handle far greater forces than earlier materials allowed. Understanding atoms also explains why some materials melt or burn while others remain stable. When a material is heated, the atoms inside it begin moving faster and faster. If the temperature becomes high enough, the atomic bonds holding the material together can loosen, causing the material to melt into a liquid or even become a gas. The behavior of atoms also explains why materials expand when heated and contract when cooled. As atoms move faster with heat, they spread slightly farther apart. When they cool down, they move less and settle closer together. Even though atoms themselves are invisible to us, their behavior determines everything about the physical world we experience. The hardness of a rock, the flexibility of rubber, the strength of steel, and the transparency of glass all come from the invisible arrangement of atoms inside those materials. This understanding of atomic structure gave scientists a powerful new ability. Instead of simply using materials found in nature, humans could begin designing materials with specific properties in mind. By controlling how atoms combine and arrange themselves, engineers could create stronger metals, lighter materials, better electronics, and more durable structures. Yet long before scientists understood atoms, early humans had already begun experimenting with materials in practical ways. They shaped stones into tools, discovered how fire could change clay into pottery, and learned which materials were best suited for different tasks. The first and most important of these early materials was stone, which gave its name to the earliest long chapter of human technological history. Clay is one of the most common materials found on Earth. It forms naturally when certain types of rock slowly break down over long periods of time. Rain, wind, and chemical reactions gradually turn solid rock into very fine particles that can mix with water to form a soft, moldable substance. When clay is wet, it behaves almost like thick mud and can be shaped easily by hand. But when it dries and is heated in fire, it becomes hard and durable. Early humans likely encountered clay in riverbanks, lake shores, and other places where water collected fine sediments. At some point, people must have noticed that when wet clay dried in the sun, it held its shape. Even more importantly, when clay was placed near fire, it became much harder and stronger than before. This discovery led to the development of pottery, one of the earliest technologies that used fire to permanently transform a material. Pottery was an important step forward in human civilization because it allowed people to create containers. Before pottery, storing liquids or grains was much more difficult. Early containers were often made from materials like animal skins, woven baskets, or hollowed-out gourds. These materials worked for certain purposes, but they were not always durable or suitable for holding liquids for long periods. Clay pots solved many of these problems. Once fired in a hot fire or simple kiln, clay pottery became strong, water-resistant, and long-lasting. People could store water, grains, oils, and cooked food in these containers. Pottery also made cooking easier because clay vessels could be placed directly over fires to heat soups, stews, and other foods. Archaeological evidence suggests that pottery began appearing in different parts of the world at various times. Some of the earliest known pottery comes from East Asia, where clay vessels were being made at least 16,000 to 18,000 years ago. Later, pottery became common in many agricultural societies as people settled into villages and needed reliable ways to store food and water. Making pottery required both skill and knowledge of materials. Clay had to be prepared carefully by removing stones and mixing it with water until it reached the right consistency. Potters would shape the clay by hand or using simple tools, forming bowls, jars, or plates. Some later cultures developed pottery wheels, which allowed potters to spin clay while shaping it, creating more symmetrical and finely crafted vessels. Once shaped, the clay objects had to dry slowly before being heated. If clay was heated too quickly while still wet, steam inside the material could cause it to crack or explode. After drying, the pottery was placed into a fire or kiln and heated to high temperatures. During this process, chemical changes occurred within the clay that made it hard and stable. Pottery also became a form of artistic expression. Many ancient cultures decorated their clay vessels with painted patterns, carved designs, or colored glazes. These decorations can still be seen today in pottery recovered from archaeological sites. In many cases, these patterns provide clues about the culture, beliefs, and daily life of the people who made them. Beyond pottery, clay was also used to make bricks for building. In regions where stone was scarce, people shaped clay into rectangular blocks and baked them in the sun or in kilns. These clay bricks could then be stacked to build houses, walls, and other structures. Some of the earliest cities in human history, such as those in ancient Mesopotamia, were built largely from clay bricks. Clay tablets also played an important role in early writing systems. In ancient civilizations like Sumer, scribes used pointed tools to press symbols into wet clay tablets. These tablets were then dried or baked, preserving the written information for long periods of time. Many of the oldest surviving written records, covering topics such as trade, laws, and stories, were preserved on clay tablets. The development of pottery and clay technology showed something important about human innovation. People were learning not only how to shape materials, but also how to transform them using heat. Fire could change the structure of clay, turning it from a soft material into something hard and durable. This discovery would eventually lead to even more dramatic transformations of materials. If clay could be hardened by fire, what would happen if rocks containing metal were placed into a hot furnace? Over time, humans began exploring this question, leading to the discovery of one of the most important materials in human history: metal. For a long time, stone and clay remained the most important materials humans could shape and transform. But eventually, people began noticing something unusual when certain rocks were placed in very hot fires. Some stones did not simply crack or crumble. Instead, small droplets of shiny material would appear inside the fire. When these droplets cooled, they formed pieces of metal. This discovery marked the beginning of metallurgy, the science and craft of extracting metals from rock. Metals are different from stone or clay because they can be melted, poured into molds, hammered into shape, and sharpened into tools. These properties made metals incredibly valuable once people learned how to work with them. One of the first metals humans used was copper. Unlike many other metals, copper sometimes appears in nature in a nearly pure form. Early humans may have discovered pieces of copper lying on the ground or exposed in rock formations. Because copper is relatively soft, it can be hammered into shape even without melting it. This allowed early metalworkers to create simple tools, jewelry, and decorative objects. Over time, people learned that heating copper made it easier to shape. When copper was placed into a fire and heated to high temperatures, it became softer and more workable. Eventually, humans discovered that copper could be melted completely and poured into molds. This allowed metalworkers to create tools and objects with shapes that would have been difficult or impossible to carve from stone. The ability to melt and shape metal represented a major technological leap. Unlike stone tools, which had to be carefully chipped into shape, metal tools could be cast into molds and then refined by hammering or sharpening. Metal tools could also be repaired or reshaped if they became dull or damaged. However, copper had an important limitation. It was softer than many types of stone. While copper tools were useful, they could bend or wear down more easily than stone blades used for heavy cutting tasks. Metalworkers eventually discovered that copper could be improved by mixing it with small amounts of another element called tin. When copper and tin are melted together, they form a new metal called bronze. Bronze is harder and stronger than pure copper, making it much better for tools, weapons, and armor. This discovery gave rise to an important period in human history known as the Bronze Age. During the Bronze Age, societies across parts of Europe, Asia, and the Middle East began producing bronze tools and weapons on a large scale. Bronze axes, knives, and spearheads were stronger and more durable than most stone tools. Farmers could clear land more efficiently, builders could shape wood more easily, and armies could equip soldiers with more reliable weapons. Bronze also allowed the creation of more complex objects. Metalworkers could pour molten bronze into molds made of clay or stone to produce tools, statues, jewelry, and decorative items. Some ancient bronze objects show remarkable craftsmanship, with detailed shapes and patterns created thousands of years ago. The production of bronze required more than just metalworking skill. Copper and tin rarely occur together in the same locations. Copper deposits might be found in one region, while tin deposits might exist hundreds or even thousands of kilometers away. This meant that bronze production encouraged long-distance trade networks. Merchants and traders began moving metals and other materials between distant regions. These trade routes connected early civilizations and allowed ideas, technologies, and cultural practices to spread. In this way, a new material, bronze, helped build connections between societies. Bronze also played an important role in early art and culture. Ancient metalworkers used bronze to create statues, musical instruments, and ceremonial objects. Some of the most famous ancient sculptures were cast in bronze using techniques that allowed artists to capture fine details in metal. Despite its advantages, bronze production still depended on access to copper and tin. If one of these metals became scarce, bronze tools could not be produced easily. This limitation eventually led to the search for another metal that was more widely available. That metal was iron. Iron exists in far greater quantities within the Earth's crust than copper or tin. However, iron is more difficult to extract from rock because it requires much higher temperatures to melt and separate from its ores. Learning how to work with iron would require new furnaces, new techniques, and new knowledge about how materials behave under extreme heat. When humans finally mastered ironworking, it would begin another major chapter in the story of materials, one that would shape civilizations for thousands of years. For a long time, stone and clay remained the most important materials humans could shape and transform. But eventually, people began noticing something unusual when certain rocks were placed in very hot fires. Some stones did not simply crack or crumble. Instead, small droplets of shiny material would appear inside the fire. When these droplets cooled, they formed pieces of metal. This discovery marked the beginning of metallurgy, the science and craft of extracting metals from rock. Metals are different from stone or clay because they can be melted, poured into molds, hammered into shape, and sharpened into tools. These properties made metals incredibly valuable once people learned how to work with them. One of the first metals humans used was copper. Unlike many other metals, copper sometimes appears in nature in a nearly pure form. Early humans may have discovered pieces of copper lying on the ground or exposed in rock formations. Because copper is relatively soft, it can be hammered into shape even without melting it. This allowed early metalworkers to create simple tools, jewelry, and decorative objects. Over time, people learned that heating copper made it easier to shape. When copper was placed into a fire and heated to high temperatures, it became softer and more workable. Eventually, humans discovered that copper could be melted completely and poured into molds. This allowed metalworkers to create tools and objects with shapes that would have been difficult or impossible to carve from stone. The ability to melt and shape metal represented a major technological leap. Unlike stone tools, which had to be carefully chipped into shape, metal tools could be cast into molds and then refined by hammering or sharpening. Metal tools could also be repaired or reshaped if they became dull or damaged. However, copper had an important limitation. It was softer than many types of stone. While copper tools were useful, they could bend or wear down more easily than stone blades used for heavy cutting tasks. Metalworkers eventually discovered that copper could be improved by mixing it with small amounts of another element called tin. When copper and tin are melted together, they form a new metal called bronze. Bronze is harder and stronger than pure copper, making it much better for tools, weapons, and armor. This discovery gave rise to an important period in human history known as the Bronze Age. During the Bronze Age, societies across parts of Europe, Asia, and the Middle East began producing bronze tools and weapons on a large scale. Bronze axes, knives, and spearheads were stronger and more durable than most stone tools. Farmers could clear land more efficiently, builders could shape wood more easily, and armies could equip soldiers with more reliable weapons. Bronze also allowed the creation of more complex objects. Metalworkers could pour molten bronze into molds made of clay or stone to produce tools, statues, jewelry, and decorative items. Some ancient bronze objects show remarkable craftsmanship, with detailed shapes and patterns created thousands of years ago. The production of bronze required more than just metalworking skill. Copper and tin rarely occur together in the same locations. Copper deposits might be found in one region, while tin deposits might exist hundreds or even thousands of kilometers away. This meant that bronze production encouraged long-distance trade networks. Merchants and traders began moving metals and other materials between distant regions. These trade routes connected early civilizations and allowed ideas, technologies, and cultural practices to spread. In this way, a new material, bronze, helped build connections between societies. Bronze also played an important role in early art and culture. Ancient metalworkers used bronze to create statues, musical instruments, and ceremonial objects. Some of the most famous ancient sculptures were cast in bronze, using techniques that allowed artists to capture fine details in metal. Despite its advantages, bronze production still depended on access to copper and tin. If one of these metals became scarce, bronze tools could not be produced easily. This limitation eventually led to the search for another metal that was more widely available. That metal was iron. Iron exists in far greater quantities within the Earth's crust than copper or tin. However, iron is more difficult to extract from rock because it requires much higher temperatures to melt and separate from its ores. Learning how to work with iron would require new furnaces, new techniques, and new knowledge about how materials behave under extreme heat. When humans finally mastered ironworking, it would begin another major chapter in the story of materials, one that would shape civilizations for thousands of years. Long before modern laboratories and industrial furnaces existed, humans were already experimenting with another remarkable material that began with something very ordinary: sand. When sand is heated to extremely high temperatures, it melts into a glowing liquid that can be shaped and then cooled into a hard, smooth, transparent substance. That substance is glass. Glass is one of the most unusual materials humans have ever learned to produce. Unlike metals or stone, glass is not arranged in neat, repeating crystal patterns at the atomic level. Instead, its structure is more disordered, almost like a frozen liquid. This unique structure gives glass several interesting properties. It can be transparent, allowing light to pass through. It can be molded when hot, and once cooled, it becomes rigid and durable. The main ingredient in most glass is silica, a compound found in sand and quartz. Silica melts at extremely high temperatures, around 1,700 degrees Celsius, or about 3,100 degrees Fahrenheit. Early furnaces rarely reached such temperatures easily, so ancient glassmakers often added other materials, such as soda ash or lime, to lower the melting point and make the process more manageable. The origins of glassmaking go back thousands of years. Archaeological evidence suggests that early glass objects appeared around 3,500 to 4,000 years ago in regions such as Mesopotamia and ancient Egypt. At first, glass was used mainly for decorative items like beads and small ornaments. These early glass pieces were often opaque or colored rather than transparent. One ancient story, recorded by the Roman writer Pliny the Elder around the 1st century CE, describes a group of merchants resting on a beach and placing cooking pots over blocks of natural soda. According to the story, the heat from the fire caused the soda and sand beneath it to melt together, forming glass. While historians are not certain that this story is literally true, it reflects the general idea that glassmaking began through accidental discoveries involving heat, sand, and minerals. By around 1500 BCE, Egyptian artisans had learned to produce small glass vessels using a technique called core forming. In this process, a clay core was shaped into the form of a container. Molten glass was then wrapped around the core and shaped while hot. Once the glass cooled, the clay core could be removed, leaving a hollow glass vessel. Glassmaking technology improved greatly during the Roman Empire. Around the 1st century BCE, glassblowing was invented, likely in the eastern Mediterranean region. Glassblowing allowed craftsmen to inflate molten glass using a long metal pipe, shaping it into bottles, bowls, and other containers. This technique made glass production much faster and more flexible. Roman glassmakers became highly skilled at producing glass objects in large quantities. They also improved glass transparency, allowing for the creation of clearer vessels and windows. Although Roman windows were often small and slightly cloudy compared with modern glass, they represented an important step in architecture and building design. After the fall of the Roman Empire, glassmaking continued in various regions, particularly in the Middle East and later in medieval Europe. One of the most famous centers of glass production emerged in Venice during the Middle Ages. Beginning in the 1200s, Venetian glassmakers on the island of Murano developed advanced techniques for producing high-quality glass. Murano glass became famous for its clarity, color, and intricate craftsmanship. Glass became even more important when it was used in scientific instruments. In the late 1500s and early 1600s, improvements in glass lens making led to the development of the telescope and the microscope. The Italian scientist Galileo Galilei used early telescopes around 1609 to observe the moons of Jupiter and the phases of Venus, providing evidence that supported the heliocentric model of the solar system. Around the same time, the Dutch scientist Antony van Leeuwenhoek used carefully crafted glass lenses to build powerful microscopes. In the 1670s, he observed tiny organisms in water, what we now call bacteria and protozoa, for the first time in human history. Without clear glass lenses, these discoveries would not have been possible. Glass also became essential in chemistry laboratories, where scientists needed containers that could withstand heat and chemical reactions while allowing researchers to see what was happening inside. Test tubes, flasks, and other laboratory glassware remain essential tools in modern science. In architecture, glass allowed buildings to capture natural light. Large windows became more common during the 19th and 20th centuries as glass manufacturing improved. Today, entire skyscrapers can be covered with glass panels that reflect sunlight while protecting the interior from weather. Modern glass production uses large industrial furnaces that operate at temperatures above 1,500 degrees Celsius. One of the most common methods for producing flat glass today is called the float glass process, invented in the 1950s by British engineer Sir Alistair Pilkington. In this process, molten glass is poured onto a bath of molten tin, where it spreads out into a perfectly smooth sheet before cooling. Glass is now used in countless applications, from smartphone screens and optical fibers to scientific equipment and spacecraft windows. Some types of glass are strengthened chemically or thermally to resist breaking, while others are designed to filter specific wavelengths of light. This long history shows how a simple material made from sand became one of the most important tools for science, architecture, and technology. Yet while glass helped humans see the world more clearly, through windows, telescopes, and microscopes, another material was quietly helping humans build the structures of civilization itself. That material was concrete, a mixture of stone, sand, and cement that would eventually allow humans to construct roads, bridges, dams, and entire cities. While glass helped humans see farther and understand the world more clearly, another material was becoming the backbone of human construction. That material was concrete. Today, concrete is so common that it often goes unnoticed, yet it is the most widely used building material on Earth. Roads, bridges, tunnels, dams, apartment buildings, and entire city foundations depend on it. In fact, humans now produce more concrete each year than any other manufactured material except water. But the idea behind concrete is surprisingly ancient, and its development spans thousands of years of experimentation, engineering, and scientific discovery. At its most basic level, concrete is a mixture of small stones, sand, water, and a binding substance called cement. When cement reacts with water through a chemical process called hydration, it hardens and locks the sand and stones together into a solid mass. The resulting material becomes extremely strong under compression, meaning it can hold enormous weight pressing down on it. This simple concept, gluing together small pieces of rock with a chemical binder, turned out to be one of the most powerful ideas in the history of construction. The earliest forms of concrete-like materials appeared thousands of years ago. Archaeological evidence suggests that as early as 6,500 BCE, some communities in the region of modern-day Syria and Jordan were using mixtures of lime and crushed stone to create primitive floors and structures. Later, ancient Egyptians used mixtures of gypsum and lime as mortars to hold together the massive stone blocks used in the pyramids, some of which were built around 2,600 BCE. These early materials were not quite the same as modern concrete, but they demonstrated an important principle. Combining crushed stone with a chemical binder could produce a durable building material. The civilization that truly advanced concrete technology was ancient Rome. Around the 3rd century BCE, Roman builders began using a special mixture that included lime, volcanic ash, sand, and broken stones. The volcanic ash, known as pozzolana, came from volcanic regions around the Bay of Naples. When mixed with lime and water, this ash created a chemical reaction that produced a very strong and durable material. Roman engineers quickly realized that this new type of concrete could be used to construct large structures far more efficiently than stacking heavy stone blocks alone. Roman concrete allowed builders to create arches, domes, and massive walls that would have been extremely difficult to construct using traditional stone techniques. One of the most famous examples is the Pantheon in Rome, completed around 126 CE during the reign of Emperor Hadrian. The Pantheon's dome remains the largest unreinforced concrete dome in the world, nearly 2,000 years later. Its design demonstrates how Roman engineers carefully controlled the composition of their concrete, using lighter materials toward the top of the dome to reduce weight while maintaining strength. Roman concrete was also used to build harbors, bridges, aqueducts, and roads throughout the Roman Empire. In some cases, Roman concrete structures have survived longer than modern concrete buildings. Researchers studying ancient Roman harbor structures have discovered that the chemical reactions between volcanic ash, lime, and seawater actually strengthen the concrete over time, making it incredibly durable. Modern scientists continue studying Roman concrete formulas to understand why they have lasted so long. After the fall of the Roman Empire around the 5th century CE, much of the knowledge about large-scale concrete construction was gradually lost in Europe. Builders returned to using stone and brick as their primary materials. For many centuries, concrete was rarely used on the same scale as it had been in Roman times. The modern era of concrete began in the 18th and 19th centuries, when scientists and engineers started rediscovering and improving cement chemistry. In 1824, an English bricklayer named Joseph Aspdin patented a new type of cement he called Portland cement, named after Portland stone, a type of building stone popular in England. Aspdin's cement was created by heating limestone and clay together at high temperatures and then grinding the resulting material into a fine powder. When mixed with water, this powder hardened into a strong binder. Portland cement quickly became the foundation of modern concrete production. Unlike earlier lime-based materials, Portland cement could set and harden more quickly while producing stronger bonds between particles of sand and gravel. This made it ideal for large-scale construction during the rapidly growing cities of the 19th and 20th centuries. Another major improvement came with the invention of reinforced concrete. Although concrete is very strong when compressed, it is relatively weak when stretched or pulled apart. In the mid-1800s, engineers began embedding iron or steel bars inside concrete structures to strengthen them against tension forces. This technique, known as reinforced concrete, allowed builders to combine the compressive strength of concrete with the tensile strength of steel. One of the pioneers of reinforced concrete was the French gardener Joseph Monnier, who patented a system in 1867 that used iron mesh embedded within concrete to create stronger plant containers. Engineers soon realized that the same idea could be used to build stronger bridges, buildings, and other structures. By the late 19th century, reinforced concrete was being used widely in construction projects across Europe and the United States. Reinforced concrete transformed architecture and engineering. It allowed buildings to rise higher, bridges to span longer distances, and dams to hold back enormous volumes of water. Famous structures such as the Hoover Dam in the United States, completed in 1936, required millions of tons of concrete poured into massive forms. The dam stands over 220 meters tall and remains one of the most impressive concrete engineering projects ever built. Today, concrete continues to evolve. Engineers develop new mixtures that include additives to improve strength, flexibility, and resistance to cracking. Some modern concretes can heal small cracks automatically when exposed to moisture, thanks to special bacteria or chemical additives mixed into the material. Other types of concrete are designed to absorb pollution or reflect sunlight to reduce urban heat. Despite its usefulness, concrete also presents challenges. Producing cement requires heating limestone to temperatures around 1,450 degrees Celsius, a process that consumes large amounts of energy and releases carbon dioxide into the atmosphere. As a result, scientists and engineers are researching new types of cement and alternative materials that could reduce the environmental impact of concrete production. Concrete demonstrates how a relatively simple mixture of materials, stone, sand, water, and cement, can reshape entire civilizations when combined with engineering knowledge. But while concrete allowed humans to build massive structures on the ground, another group of materials was quietly changing daily life in a different way. These materials were flexible, lightweight, and capable of being woven into fabrics. They would become essential not for buildings, but for clothing, trade, and industry. Those materials were textiles. While materials like stone, metal, glass, and concrete shaped the structures humans built around them, another group of materials quietly shaped something just as important: how people lived, traveled, and protected themselves from the environment. These were textile materials, fibers that could be spun into threads and woven into fabrics. Clothing, blankets, ropes, sails, and many everyday objects depended on these materials long before modern manufacturing existed. The science and history of textiles stretch back thousands of years and connect agriculture, trade, engineering, and culture. Textiles begin with fibers. A fiber is simply a very thin strand of material that is flexible enough to be twisted or woven together. Some fibers come directly from plants, others from animals, and many modern ones are made synthetically in factories. When fibers are twisted together into long strands, they form threads or yarns. These threads can then be woven, knitted, or braided into fabrics. One of the earliest and most widely used plant fibers in human history is flax, which is used to make linen. Flax fibers come from the stalk of the flax plant and have been used by humans for at least 7,000 years. Archaeologists have discovered linen fabrics in ancient Egyptian tombs dating back to around 3000 BCE. The Egyptians valued linen highly because it was lightweight and breathable, making it suitable for hot desert climates. Linen was used for clothing, sails on boats traveling along the Nile River, and even for wrapping mummies during burial rituals. Another extremely important textile fiber is wool, which comes from the hair of sheep and certain other animals. Unlike plant fibers that must be harvested from crops, wool grows naturally on animals and can be collected through shearing. Wool fibers are naturally crimped, which means they bend slightly along their length. This structure allows wool threads to trap air, providing excellent insulation. Because of this property, wool clothing keeps people warm even in cold or damp conditions. Wool became especially important in regions with cooler climates, such as parts of Europe and Central Asia. By around 2000 BCE, sheep were widely domesticated, and wool production had become an important part of agricultural life. Entire economies in medieval Europe were built around wool trade. England, for example, exported large amounts of wool to continental Europe during the Middle Ages, where it was woven into cloth by skilled textile workers. Another famous textile fiber is silk, which has a very different origin. Silk is produced by silkworms, the larvae of a species of moth called Bombyx mori. As part of their life cycle, silkworms spin protective cocoons made from a continuous thread of silk fiber that can reach up to 1 kilometer in length. Humans learn to carefully unravel these cocoons and spin the fibers into silk thread. Silk production began in ancient China at least 4,000 to 5,000 years ago. For many centuries, the Chinese closely guarded the secret of silk production, making silk one of the most valuable luxury materials in the ancient world. The famous Silk Road trade routes that connected China with the Middle East and Europe were named after this valuable fabric. Along these routes, silk was traded alongside spices, precious metals, and other goods, linking distant civilizations through commerce. Cotton eventually became one of the most widely used textile fibers in the world. Cotton fibers grow around the seeds of the cotton plant and are soft, lightweight, and easy to spin into thread. Evidence of cotton textiles dates back to around 5000 BCE in regions such as the Indus Valley, located in present-day Pakistan and northwest India. Cotton fabrics were comfortable in warm climates and could be dyed in many colors. During the 18th and 19th centuries, cotton played a central role in the Industrial Revolution. New machines such as the spinning jenny, invented by James Hargreaves around 1764, and the power loom, improved by Edmund Cartwright in the 1780s, allowed cotton fibers to be spun and woven much faster than by hand. Textile mills powered by water wheels and later steam engines transformed fabric production into a major industry. Textile manufacturing helped drive the growth of factories and urban centers during the Industrial Revolution. Cotton cloth could be produced in enormous quantities, lowering costs and making clothing more affordable for growing populations. However, the expansion of cotton production was also deeply connected to global trade networks and, tragically, to systems of forced labor and slavery in parts of the world. Beyond plant and animal fibers, the 20th century introduced entirely new kinds of textile materials, synthetic fibers. Unlike natural fibers, which come from plants or animals, synthetic fibers are made from chemical compounds created in laboratories and factories. One of the earliest synthetic fibers was nylon, developed in 1935 by the American chemist Wallace Carothers while working for the DuPont Company. Nylon was strong, lightweight, and flexible, making it useful for many applications. It was first used in products such as toothbrush, bristles, and stockings. But during World War II, it became important for manufacturing parachutes, ropes, and other military equipment. After the war, synthetic fibers expanded into clothing, carpets, and industrial materials. Other synthetic fibers soon followed. Polyester, developed in the 1940s and widely used by the 1950s, became one of the most common textile materials in the world. Polyester fabrics resist wrinkles, dry quickly, and are durable under repeated use. Today, many garments contain blends of natural and synthetic fibers to combine the advantages of each. Textiles demonstrate how materials can shape everyday life in ways that are both practical and cultural. Clothing protects people from heat, cold, and weather, but it also expresses identity, tradition, and social status. The fibers used in textiles, whether linen in ancient Egypt, silk in imperial China, wool in medieval Europe, or synthetic fabrics in modern fashion, tell stories about the technologies and societies that produce them. While textiles shaped clothing and trade, another material that humans had used since ancient times continued to play a central role in construction, tools, and transportation. That material was wood, one of the oldest and most versatile natural materials ever used by human societies. Long before humans learned to smelt metals or mix concrete, wood was already one of the most important materials shaping daily life. Wood is a natural material that comes from trees, and it has been used by humans for hundreds of thousands of years. Early humans likely used fallen branches or simple wooden sticks long before they developed complex tools. Once stone tools appeared during the Stone Age, wood could be cut, carved, and shaped much more easily, allowing humans to build shelters, weapons, tools, and eventually boats and buildings. One reason wood became such a central material is because of its unique combination of strength and lightness. Wood is strong enough to support weight, but it is much lighter than stone or metal. This made it ideal for many practical uses, from building frames for houses to constructing wheels and carts. Wood is also relatively easy to work with using simple tools. A sharp stone blade or later a metal axe could cut or shape wood into useful forms. The structure of wood explains many of these properties. Wood is made from long, tube-like cells that once carried water and nutrients through a living tree. These cells grow in organized patterns that give wood its grain. Because of this structure, wood is strong when forces push along the direction of the grain, but weaker when forces push across it. Skilled builders learned to use this property by arranging wooden beams in ways that made structures stronger and more stable. Different types of trees produce different kinds of wood, each with its own characteristics. Hardwoods, such as oak, maple, and walnut, come from trees that grow more slowly and often produce denser, stronger wood. Softwoods, such as pine and cedar, come from faster-growing trees and are usually lighter and easier to cut. Both types have been used throughout history depending on the needs of builders and craftsmen. Wood played a major role in early transportation technologies. One of the earliest wheels ever discovered, dating to around 3,500 BCE in Mesopotamia, was carved from solid pieces of wood. These early wheels were heavy, but allowed carts and wagons to move goods across land far more efficiently than carrying them by hand. Wooden wheels later evolved into lighter designs using spokes, which made vehicles faster and easier to pull by animals. Wood was also essential in the construction of ships and boats. Early dugout canoes made by hollowing out large tree trunks have been found in archaeological sites dating back at least 8,000 years. As shipbuilding techniques improved, wooden planks were joined together to form larger vessels, capable of traveling long distances across seas and oceans. Entire civilizations depended on wooden ships for trade, exploration, and warfare. For example, the Vikings of Scandinavia, around the 9th to 11th centuries, built long ships using carefully shaped oak planks. These ships were both strong and flexible, allowing them to travel across the rough waters of the North Atlantic. Similarly, large wooden sailing ships played a central role in the age of exploration during the 15th and 16th centuries, when European navigators such as Christopher Columbus and Ferdinand Magellan crossed vast oceans. Wood also served as the primary structural material for buildings in many parts of the world. In regions with abundant forests, houses, barns, and temples were often constructed almost entirely from timber. Traditional Japanese architecture, for example, uses intricate wooden joinery techniques that allow large structures to be built without nails. Some of these buildings have stood for hundreds of years, despite earthquakes and changing weather conditions. In addition to its strength and workability, wood had another extremely important use: fuel. For thousands of years, wood was the primary source of energy for heating, cooking, and metalworking. When wood burns, it releases chemical energy stored during the tree's growth through photosynthesis. Early blacksmiths and metalworkers often converted wood into charcoal by heating it in low oxygen environments. Charcoal burns hotter and cleaner than raw wood, making it ideal for furnaces used in metal production. Despite its many advantages, wood also has limitations. It can rot over time when exposed to moisture and microorganisms. Insects such as termites can damage wooden structures. Wood can also burn, which makes fire a constant risk in wooden buildings. For these reasons, engineers and builders have often sought materials that can perform similar functions while resisting these problems. Even so, wood remains widely used today. Modern construction still relies on timber for framing houses, furniture, flooring, and many other products. Engineered wood products such as plywood and laminated timber combine layers of wood in ways that increase strength and stability. Some modern buildings are even exploring the use of massive engineered wood beams to construct tall structures that rival steel and concrete buildings. Wood demonstrates how a natural material can remain important across thousands of years of technological progress. From simple tools and shelters to ships that crossed oceans and homes that shelter millions of people today, wood has been one of humanity's most dependable materials. Yet as the 19th and 20th centuries progressed, scientists and engineers began developing materials that did not exist in nature at all. These materials were created entirely through chemistry and industrial manufacturing, and they would soon become some of the most common materials used in modern life. These new substances were known as plastics. By the late 19th century, scientists and engineers had become very skilled at working with natural materials, such as wood, metals, glass, and stone. However, the rapid growth of industry created a new challenge. Many natural materials were either limited in supply or expensive to produce. For example, ivory from elephant tusks was widely used for items like billiard balls, piano keys, and decorative objects. As demand increased, people began searching for alternative materials that could replace these scarce resources. This search led to one of the most important developments in the history of materials, the invention of plastics. Unlike materials such as stone, wood, or metal, plastics are not found in nature. They are synthetic materials created by chemists through controlled chemical reactions. The word plastic comes from a Greek word meaning able to be shaped, which reflects one of the material's most useful properties. When heated, many plastics can be softened and molded into almost any shape, and when they cool, they become solid again. The first widely recognized plastic was invented in 1869 by an American inventor named John Wesley Hyatt. At the time, a company had offered a large prize for anyone who could find a substitute for ivory in the production of billiard balls. Hyatt experimented with a material called cellulose nitrate, which was derived from plant fibers. By combining it with camphor, he created a new substance called celluloid. Celluloid could be molded into shapes and polished to resemble ivory or other materials. It soon found uses in combs, photographic film, toys, and many other products. Although celluloid was useful, it was also flammable and somewhat unstable. Scientists continued searching for better synthetic materials. In 1907, a Belgian-born chemist named Leo Beekeland invented the first fully synthetic plastic, called bakelite. Unlike celluloid, bakelite was created entirely from chemical compounds rather than modified natural materials. It was made by combining phenol and formaldehyde under heat and pressure. Bakelite had several remarkable properties. It was strong, resistant to heat, and an excellent electrical insulator. These qualities made it extremely valuable during the early 20th century when electrical technology was expanding rapidly. Bakelite was used to make radio casings, telephone parts, electrical switches, and many household items. It marked the beginning of a new era in which materials could be designed and produced through chemistry rather than simply discovered in nature. During the 20th century, plastic technology expanded rapidly. Chemists began developing many different types of plastic materials with a wide range of properties. One of the key ideas behind plastics is the formation of polymers. A polymer is a long chain made by connecting many smaller molecules together. These chains can be arranged in different ways, giving plastics their unique characteristics. One of the most important plastics developed during this time was polyethylene, first produced accidentally in 1933 by chemists working for the British company Imperial Chemical Industries. Polyethylene is lightweight, flexible, and resistant to moisture, making it ideal for packaging materials such as plastic bags and containers. Today it remains one of the most widely used plastics in the world. Another important plastic is polyvinyl chloride, often known as PVC. Developed in the early 20th century but widely used after the 1920s, PVC can be either rigid or flexible, depending on how it is manufactured. It is used in pipes, flooring, electrical insulation, and many other construction materials. Polystyrene, another plastic invented in the early 20th century, became widely used for packaging and insulation. When expanded with air bubbles, it forms a lightweight foam often used in protective packaging and disposable containers. The development of plastics accelerated during World War II, when shortages of natural materials forced scientists to create new synthetic alternatives. Nylon, invented in 1935 by the American chemist Wallace Carruthers, became one of the most famous examples. Nylon fibers were strong, flexible, and lightweight, making them useful for parachutes, ropes, and later clothing and textiles. After the war, plastics spread rapidly into everyday life. Plastic containers, toys, kitchen tools, electronic housings, and countless other products became common. Plastics were cheap to produce, easy to shape, and resistant to corrosion. These properties made them incredibly useful for manufacturing and consumer goods. By the late 20th century, plastics had become one of the most widely used materials on Earth. Every year, hundreds of millions of tons of plastic are produced worldwide. They are used in packaging, medical equipment, vehicles, electronics, clothing, and construction. However, the widespread use of plastics has also created new environmental challenges. Many plastics do not break down easily in nature. Instead, they can persist for decades or even centuries. Plastic waste accumulating in oceans and landfills has become a major environmental concern. Scientists are now working to develop biodegradable plastics and improved recycling methods to reduce these impacts. Despite these challenges, plastics remain an important example of how humans can design entirely new materials to solve problems. They represent a shift from using materials that nature provides to creating materials that are engineered for specific purposes. At the same time, plastics were transforming everyday objects. Another metal was becoming increasingly important for modern engineering. This metal was strong, lightweight, and resistant to corrosion. It would become essential for airplanes, vehicles, and modern construction. That metal was aluminum. For most of human history, aluminum was completely unknown as a usable metal, even though it is one of the most abundant elements in the Earth's crust. In fact, aluminum makes up roughly 8% of the Earth's outer layer, making it more common than iron. Yet for thousands of years, humans could not use aluminum because it does not appear naturally as pure metal. Instead, aluminum is tightly bound within minerals, such as bauxite and clay. Extracting it requires complex chemical processes and large amounts of electricity, technologies that did not exist until relatively recently. The element aluminum was first identified in the early 19th century. In 1808, the British chemist Sir Humphry Davy proposed the existence of a new metal within certain minerals and suggested the name aluminum, later spelled aluminium in some countries. However, Davy was not able to isolate the pure metal itself. It was not until 1825 that the Danish scientist Hans Christian Ørsted successfully produced small amounts of aluminum metal by chemically reducing aluminum chloride. Even then, aluminum remained extremely rare and expensive. Producing small samples required complicated chemical reactions and produced only tiny amounts of the metal. During the mid-19th century, aluminum was considered more valuable than silver or gold. In fact, during the 1850s, French Emperor Napoleon III reportedly reserved aluminum tableware for his most honored guests, while other visitors had to use ordinary silver utensils. This situation changed dramatically in 1886 with one of the most important discoveries in the history of industrial chemistry. In that year, two young scientists working independently, Charles Martin Hall in the United States and Paul Héroult in France, discovered a new process for extracting aluminum from bauxite using electricity. Their method, now known as the Hall-Héroult process, involves dissolving aluminum oxide in molten cryolite and passing a powerful electric current through the mixture. The electric current separates the aluminum from the oxygen, producing molten aluminum metal at the bottom of the container. This process requires extremely high temperatures, around 950 degrees Celsius, and large amounts of electricity. However, it allows aluminum to be produced in large quantities far more efficiently than earlier chemical methods. The invention of the Hall-Héroult process quickly transformed aluminum from a rare laboratory curiosity into a practical industrial metal. Within a few decades, aluminum production expanded rapidly as factories were built near large sources of electricity, especially hydroelectric power plants. Regions with abundant hydroelectric energy, such as parts of Canada and Norway, became major centers of aluminum production. One reason aluminum became so valuable in engineering is its unusual combination of properties. Aluminum is much lighter than steel, weighing only about 1/3 as much. At the same time, when alloyed with small amounts of other elements such as copper, magnesium, or silicon, aluminum can become quite strong. This combination of strength and lightness makes aluminum extremely useful for transportation technologies. The rise of aviation during the early 20th century relied heavily on aluminum alloys. Aircraft must be strong enough to withstand enormous forces during flight, while remaining light enough to lift off the ground. Early airplane builders quickly discovered that aluminum alloys offered an ideal balance of strength and weight. One important aluminum alloy, known as duralumine, was developed around 1909 by the German metallurgist Alfred Wilm. Duralumine contains small amounts of copper, magnesium, and manganese, which significantly increased its strength while maintaining its lightweight nature. This alloy was used extensively in early aircraft construction and helped advance the development of aviation. Aluminum also became widely used in transportation beyond airplanes. Automobiles, trains, ships, and bicycles often include aluminum components because they reduce overall weight while maintaining structural strength. Lighter vehicles generally use less energy to move, which improves fuel efficiency and performance. Another useful property of aluminum is its resistance to corrosion. When aluminum is exposed to air, it quickly forms a thin layer of aluminum oxide on its surface. This layer protects the metal beneath it from further corrosion, unlike iron, which forms rust that can gradually destroy the metal. Because of this protective oxide layer, aluminum can be used outdoors and in environments where moisture might damage other metals. Aluminum is also an excellent conductor of electricity and heat. Although copper conducts electricity slightly better, aluminum is lighter and less expensive, which makes it useful for electrical transmission lines that carry power over long distances. Many overhead power lines are made from aluminum cables, reinforced with steel cores, to provide additional strength. Another advantage of aluminum is that it can be recycled very efficiently. Recycling aluminum requires only about 5% of the energy needed to produce new aluminum from raw ore. Because of this, aluminum recycling has become an important part of modern materials management. Beverage cans, automotive parts, and construction materials are often collected and melted down to produce new aluminum products. Today, aluminum is used in a wide range of industries. It appears in aircraft, vehicles, kitchen utensils, packaging materials, electronics, and building structures. The shiny foil used for food packaging is made from extremely thin sheets of aluminum rolled to thicknesses of only a few micrometers. Aluminum shows how advances in science and engineering can transform a common element into a critical industrial material. But while aluminum helped make transportation lighter and more efficient, another material was quietly becoming the foundation of modern electronics. That material came from a simple element found in sand and rock, yet it would eventually power computers, smartphones, and the digital world. That material is silicon. Silicon is one of the most important materials in the modern world, even though most people rarely think about it. Like aluminum, silicon is extremely common in the Earth's crust. In fact, it is the second most abundant element in the crust after oxygen. Silicon is found in many types of rock and sand, especially in a compound called silicon dioxide, which forms quartz and much of the sand found on beaches and deserts. For thousands of years, humans used materials containing silicon without understanding the element itself. Sand was used to make glass, stone tools often contained quartz, and clay used for pottery included many silicon-based minerals. But the pure element silicon was not isolated until the early 19th century. In 1824, the Swedish chemist Jöns Jacob Berzelius succeeded in producing relatively pure silicon by heating potassium with silicon fluoride. Although the early samples were not perfectly pure, Berzelius demonstrated that silicon was a distinct chemical element with its own properties. At the time, however, scientists had little idea that silicon would eventually become the foundation of modern electronics. One of the most important properties of silicon is that it behaves as a semiconductor. This means that it conducts electricity under certain conditions, but can also act as an insulator under other conditions. In simple terms, a semiconductor can control the flow of electrical current. This ability makes semiconductors extremely useful in electronic devices. For many years, scientists studied semiconductors only as scientific curiosities. But during the early 20th century, engineers began experimenting with semiconductor materials for electronic components. Early devices called crystal detectors were used in radio receivers to convert radio signals into sound. The real breakthrough came in 1947 at Bell Laboratories in the United States. 3 scientists, John Bardeen, Walter Brattain, and William Shockley, developed the first working transistor. The transistor is a small electronic device that can amplify or switch electrical signals. Their first transistor used a material called germanium, another semiconductor element. Soon afterward, researchers discovered that silicon was even better suited for electronic devices than germanium. Silicon could operate at higher temperatures and was more stable in many environments. During the 1950s, engineers began building transistors and other electronic components using silicon. The development of silicon-based electronics led directly to the invention of the integrated circuit in the late 1950s. Engineers such as Jack Kilby at Texas Instruments and Robert Noyce at Fairchild Semiconductor developed ways to place multiple electronic components, transistors, resistors, and capacitors, onto a single piece of semiconductor material called a chip. These chips could perform complex electronic functions in extremely small spaces. Instead of wiring together thousands of individual components, engineers could design entire circuits directly on a silicon wafer. This innovation dramatically reduced the size, cost, and power consumption of electronic devices. Silicon chips soon became the heart of computers. Early computers built during the 1940s and 1950s used vacuum tubes, which were large, fragile, and consumed enormous amounts of power. Transistors and integrated circuits made it possible to build smaller, faster, and more reliable computers. As semiconductor technology improved, the number of transistors that could fit onto a single chip increased rapidly. In 1965, Intel co-founder Gordon Moore observed that the number of transistors on integrated circuits seemed to double roughly every 2 years. This observation became known as Moore's Law and guided much of the development of computer technology for decades. Modern microprocessors now contain billions of tiny transistors packed into chips only a few centimeters across. These chips control everything from smartphones and laptops to cars, medical equipment, and communication satellites. Without silicon-based semiconductors, the digital world as we know it would not exist. Manufacturing these chips requires extremely advanced technology. Silicon is first purified into nearly perfect crystals using methods such as the Czochralski process, developed by Polish scientist Jan Czochralski in 1916. Large cylindrical crystals of silicon are slowly grown from molten silicon and then sliced into thin wafers. These wafers serve as the base for electronic circuits. The circuits themselves are created through a process called photolithography, which uses light to project patterns onto the wafer. Layers of materials are deposited, etched, and treated chemically to build microscopic electronic structures. Some features on modern chips are smaller than 10 nanometers, tens of thousands of times thinner than a human hair. The importance of silicon to modern technology is reflected in the name Silicon Valley, the region in California where many major semiconductor and computer companies developed during the late 20th century. Today, silicon remains the most widely used semiconductor material, although researchers are also exploring alternatives such as gallium nitride and silicon carbide for specialized applications. Silicon demonstrates how a simple element found in sand can become the foundation of a technological revolution. It connects the natural world with the digital systems that shape modern communication, computing, and scientific research. But silicon is only one example of how scientists and engineers continue to develop new materials with remarkable properties. In recent decades, researchers have begun designing materials that combine multiple substances together in carefully engineered structures. These materials, known as composites, can be stronger, lighter, and more versatile than traditional materials alone. As scientists and engineers continued learning how materials behave at the microscopic level, they began exploring a powerful idea. Instead of relying on a single material, what if different materials could be combined together to create something stronger, lighter, or more durable than either material alone? This idea led to the development of composite materials. A composite is simply a material made by combining two or more different substances, so that each contributes useful properties to the final product. The materials remain distinct inside the composite, but together they create a structure that performs better than either material could on its own. Nature itself uses this idea in many biological structures. For example, bone is a natural composite made of hard mineral crystals embedded in a flexible protein structure. This combination allows bones to be strong while still resisting sudden fractures. One of the earliest man-made composite materials was reinforced mud brick. Ancient builders often mixed straw or plant fibers into wet clay before forming bricks. When the bricks dried, the fibers helped hold the clay together and reduced cracking. This simple composite technique was used in many ancient civilizations, including those in Mesopotamia and Egypt. Modern composite materials, however, became far more advanced during the 20th century. One of the first widely used engineered composites was fiberglass. Fiberglass was developed during the 1930s when researchers discovered that extremely thin strands of glass could be drawn into fibers and combined with plastic resins to form a strong, lightweight material. Glass fibers themselves are surprisingly strong when stretched. When these fibers are embedded within a hardened plastic resin, they form a composite that is much stronger than the resin alone. Fiberglass became widely used during World War II for military equipment and later expanded into many civilian applications. Today, fiberglass appears in boats, automobile bodies, insulation materials, and even some building structures. It is resistant to corrosion, relatively lightweight, and can be molded into complex shapes. Because fiberglass does not rust like steel or rot like wood, It can be useful in environments where moisture or chemicals might damage other materials. An even stronger type of composite material is carbon fiber. Carbon fiber is made by heating certain synthetic fibers, often derived from polymers such as polyacrylonitrile, to extremely high temperatures, sometimes above 1,000 degrees Celsius, in carefully controlled environments. During this process, most of the non-carbon atoms are removed, leaving behind extremely strong strands of nearly pure carbon. These carbon fibers are then woven into fabrics and embedded within plastic resins to create carbon fiber composites. The resulting material is incredibly strong for its weight, often stronger than steel, but far lighter. Because of this property, carbon fiber composites are widely used in industries where reducing weight is extremely important. Modern aircraft, for example, rely heavily on carbon fiber composites. The Boeing 787 Dreamliner, introduced in 2011, uses carbon fiber materials for roughly half of its structural components. These lighter materials allow aircraft to burn less fuel while maintaining strength and safety. Carbon fiber is also widely used in racing bicycles, high-performance automobiles, sports equipment, and spacecraft components. In space exploration, reducing weight is especially critical because launching mass into orbit requires enormous amounts of energy. Lightweight composite materials allow spacecraft to carry more equipment while staying within launch limits. Another interesting class of composite materials is reinforced concrete, which was mentioned earlier in the discussion of construction materials. In reinforced concrete, steel bars are embedded inside concrete structures. The steel provides tensile strength, resistance to pulling forces, while the concrete provides compressive strength, resistance to crushing forces. This combination allows reinforced concrete structures to withstand complex stresses in buildings, bridges, and dams. Modern composite research continues to push materials science into new directions. Engineers now design materials at very small scales, sometimes manipulating structures measured in nanometers. One famous example is graphene, a material first isolated in 2004 by physicists Andrei Geim and Konstantin Novoselov at the University of Manchester. Graphene consists of a single layer of carbon atoms arranged in a hexagonal pattern. Although graphene is only one atom thick, it is extraordinarily strong, about 200 times stronger than steel when measured by weight. It also conducts electricity and heat extremely well. Scientists are exploring graphene for use in flexible electronics, energy storage devices, and advanced sensors. Composites demonstrate a key principle of materials science. The structure of a material often matters as much as its chemical composition. By carefully arranging fibers, layers, and bonding materials together, engineers can create materials with properties that would be impossible to achieve with a single substance alone. These advances have allowed humans to design materials for increasingly demanding environments, from the high temperatures of jet engines to the extreme vacuum of space. But as materials continue to evolve, scientists are now exploring an even smaller frontier. Instead of shaping materials at the scale of fibers or grains, researchers are beginning to design materials at the scale of individual atoms and molecules. This emerging field is known as nanomaterials, and it may shape the next generation of materials technology. In recent decades, materials science has begun exploring a scale so small that it was once impossible to imagine working at that level. This field is known as nanotechnology, and it focuses on materials measured in nanometers. A nanometer is 1/1,000,000th of a meter. To understand how small that is, consider that a human hair is roughly 80,000 to 100,000 nanometers wide. Nanomaterials involve structures that are often between 1 and 100 nanometers in size, meaning they are thousands of times smaller than the thickness of a hair. When materials are built or manipulated at this incredibly small scale, they can behave very differently from the same material in larger forms. This happens because the properties of materials depend not only on what atoms they contain, but also on how those atoms are arranged and how many atoms are exposed on the surface. At the nanoscale, the surface area of a material becomes very large compared to its overall size, which can dramatically change how it reacts with light, electricity, heat, and chemicals. Scientists began seriously exploring nanomaterials during the late 20th century, as new instruments made it possible to observe and manipulate matter at extremely small scales. One of the most important tools was the scanning tunneling microscope, invented in 1981 by physicists Gerd Binnig and Heinrich Rohrer at IBM. This device allowed researchers to visualize individual atoms on surfaces for the first time. Their work earned them the Nobel Prize in Physics in 1986. Once scientists could observe atoms directly, they began experimenting with ways to build structures at the nanoscale. One of the most famous nanomaterials discovered in the 1980s was the fullerene molecule, often called a buckyball. Fullerenes are made of carbon atoms arranged in hollow spheres that resemble the shape of a soccer ball. They were first identified in 1985 by chemists Robert Curl, Harold Kroto, and Richard Smalley, who later received the Nobel Prize in Chemistry for their discovery. Another important carbon-based nanomaterial is the carbon nanotube, discovered in 1991 by the Japanese physicist Sumio Iijima. Carbon nanotubes are tiny cylindrical structures made from rolled sheets of graphene. These tubes can be incredibly strong and conduct electricity extremely well. In fact, carbon nanotubes are among the strongest materials ever measured, with strength-to-weight ratios far greater than steel. Because of their unique properties, nanomaterials are being explored for many applications. In electronics, they may allow the creation of smaller and faster computer components. In medicine, nanoparticles can be designed to deliver drugs directly to specific cells inside the body. Researchers are studying how nanoparticles might be used to target cancer cells while minimizing damage to healthy tissue. Nanomaterials are also being used to improve everyday products. Some sunscreens contain tiny particles of titanium dioxide or zinc oxide that block harmful ultraviolet light while remaining transparent on the skin. Nanomaterials are also used in certain stain-resistant fabrics, water-repellent coatings, and stronger lightweight materials for sports equipment. In energy technology, nanomaterials may help improve batteries, solar panels, and fuel cells. Because nanostructures have such large surface areas relative to their size, they can improve chemical reactions involved in storing or converting energy. Scientists hope that nanotechnology may lead to more efficient energy systems in the future. Despite these exciting possibilities, nanotechnology also raises important questions about safety and environmental impact. Because nanoparticles are so small, they may behave differently inside living organisms or ecosystems. Researchers are studying how nanomaterials interact with biological systems to ensure that they can be used safely. The exploration of nanomaterials shows how far materials science has progressed. Early humans shaped stone tools using simple hammering techniques. Later civilizations learned to melt metals and build massive structures with concrete. Today, scientists can design materials by controlling structures at the scale of atoms and molecules. At the same time, materials science is not only about creating new materials, it is also about understanding how materials are used, reused, and eventually discarded. As modern societies produce enormous quantities of manufactured materials, from plastics and metals to electronic devices, managing the life cycle of these materials has become an important challenge. This leads to another major topic in the story of materials: recycling and the reuse of resources. As human societies began producing larger amounts of manufactured materials during the 20th century, a new challenge gradually emerged. For most of human history, materials were relatively scarce and valuable. Tools made from stone or metal were repaired and reused many times. Wooden objects were often repurposed when they wore out, and broken pottery could sometimes be crushed and used again in construction. But as industrial production expanded and materials became cheaper to manufacture, societies began producing far greater quantities of goods than ever before. This increase in production also meant that far more waste materials were being generated. Recycling is the process of collecting used materials and processing them so they can be used again to create new products. Although recycling might seem like a modern environmental idea, the practice has existed in various forms for centuries. In ancient times, metal objects were often melted down and reused because metals such as copper, bronze, and iron were valuable and difficult to produce. Archaeologists have found evidence that broken bronze tools and weapons were frequently remelted and recast into new objects in ancient civilizations. Yet, during the Industrial Revolution of the 19th century, recycling became more organized in certain industries. Scrap metal from factories, railroads, and construction sites could be collected and melted down to produce new steel or iron products. Because producing metal from scrap required less energy than extracting it from raw ore, recycling metal was both economically and practically beneficial. The 20th century saw the rapid growth of consumer goods made from materials such as aluminum, glass, paper, and plastics. As these materials became widely used, communities began developing systems to collect and reuse them. Recycling programs became especially common after the 1970s, when growing environmental awareness led governments and communities to encourage the reuse of materials instead of sending them to landfills. Some materials are particularly well suited for recycling. Aluminum, for example, can be recycled almost indefinitely without losing its quality. Producing aluminum from recycled metal requires only about 5% of the energy needed to produce aluminum from raw bauxite ore. Because of this enormous energy savings, aluminum beverage cans are among the most widely recycled consumer products. Glass is another material that can be recycled many times. When glass products are collected and crushed into small pieces called cullet, they can be melted and reformed into new glass containers or other products. Recycling glass reduces the need for raw materials, such as sand and limestone, and lowers the energy required for glass production. Paper recycling is also widely practiced. Paper is made primarily from wood fibers, and recycling paper allows those fibers to be reused several times before they become too short to form strong paper sheets. By recycling paper, fewer trees need to be cut down, and less energy and water are used in the production process. Plastics, however, present greater challenges for recycling. Many plastics contain different chemical compositions that must be separated before they can be reused. Some plastics degrade in quality each time they are recycled, meaning they cannot be reused indefinitely in the same way that metals can. As a result, scientists and engineers continue searching for improved recycling technologies and biodegradable plastic alternatives that break down more easily in the environment. Recycling is only one part of what scientists call the life cycle of materials. Every material goes through a series of stages: extraction of raw resources, manufacturing into products, used by consumers, and eventually disposal or recycling. Understanding this life cycle helps engineers design materials and products that use fewer resources and generate less waste. For example, modern engineers often design products so that materials can be separated more easily when the product reaches the end of its useful life. Electronic devices such as smartphones contain valuable metals like gold, copper, and rare earth elements. Recovering these materials through recycling helps reduce the need for new mining operations and preserves valuable resources. The concept of a circular economy has also become an important goal in materials science and environmental policy. In a circular economy, materials are reused, repaired, and recycled as much as possible, rather than being discarded after a single use. This approach aims to keep materials circulating through the economy for longer periods while reducing waste and environmental impact. As global populations grow and demand for technology increases, managing material resources responsibly will become increasingly important. Many modern technologies rely on rare elements that are found only in certain parts of the world. Ensuring stable supplies of these materials requires careful planning, recycling, and international cooperation. At the same time, scientists are continuing to explore entirely new materials that may reshape industries in the future. Advanced alloys, smart materials that respond to environmental changes, and materials designed at the nanoscale may allow engineers to build stronger structures, more efficient energy systems, and new technologies that have not yet been imagined. The long history of materials, from stone tools to nanotechnology, shows how deeply human progress depends on understanding and shaping the substances that make up the physical world. Each new discovery about materials has opened doors to new tools, new industries, and new ways of living. As materials science has advanced, researchers have begun developing materials that can actively respond to their surroundings rather than simply remaining static objects. These are known as smart materials. Unlike traditional materials such as stone or steel, which behave the same way regardless of their environment, smart materials can change their shape, stiffness, color, or electrical behavior when exposed to changes in temperature, pressure, electricity, or light. One well-known example of a smart material is the shape memory alloy. These are special metal mixtures that can return to their original shape after being bent or deformed. One of the most common shape memory alloys is a mixture of nickel and titanium called nitinol, a name derived from Nickel Titanium Naval Ordnance Laboratory, where it was developed in the early 1960s. Shape memory alloys work because of the way their internal crystal structure changes with temperature. When the metal is cool, it can be bent or stretched into a new shape, but when it is heated, the atomic structure rearranges itself and the material remembers its original form, snapping back to its previous shape. This unusual property has made shape memory alloys useful in medical devices, such as stents, which can be inserted into blood vessels in a compressed form and then expand to their intended shape once inside the body. Another type of smart material is piezoelectric material. The word piezoelectric comes from the Greek word for to press. These materials generate an electric charge when they are squeezed or bent. The effect also works in reverse. When electricity is applied to the material, it changes shape slightly. Piezoelectric materials were first discovered in 1880 by two French physicists, Pierre Curie and Jacques Curie. Today, they are used in a wide variety of technologies. For example, piezoelectric sensors are used in microphones, guitar pickups, and ultrasound machines. They can convert vibrations into electrical signals that can be measured or amplified. In everyday life, piezoelectric materials are also used in devices such as electronic lighters and quartz watches. In a quartz watch, a tiny crystal vibrates when electricity passes through it, producing an extremely precise frequency that helps keep accurate time. Another fascinating group of smart materials is electrochromic materials, which can change color when electricity is applied. These materials are used in certain types of smart windows that can automatically darken in bright sunlight to reduce heat and glare inside buildings. Similar technology is used in auto-dimming rear-view mirrors in modern cars, which darken when bright headlights from vehicles behind are detected. Smart materials are also used in aerospace engineering. Some aircraft components are designed with materials that can adjust their shape slightly during flight to improve aerodynamics. Researchers are exploring materials that could allow airplane wings to subtly change shape depending on speed and air pressure, increasing fuel efficiency. Another emerging field in materials science involves self-healing materials. These materials are designed to repair small cracks or damage automatically. In some experimental materials, tiny capsules filled with special chemicals are embedded within the structure. If a crack forms, the capsules break open and release the chemicals, which then react and harden to seal the damage. Self-healing materials could be especially useful in structures where repairs are difficult, such as bridges, pipelines, or spacecraft. By repairing small cracks before they grow larger, these materials could greatly extend the lifespan of important infrastructure. Materials science also plays a critical role in modern energy technologies. Batteries, solar panels, and fuel cells all depend on carefully engineered materials to store or convert energy efficiently. Lithium-ion batteries, for example, rely on materials that allow lithium ions to move back and forth between electrodes during charging and discharging cycles. Improvements in battery materials have helped power the rise of electric vehicles and portable electronics. Solar panels rely on semiconductor materials such as silicon to convert sunlight into electricity. When photons from sunlight strike the surface of the semiconductor, they release electrons that create an electrical current. Scientists are now exploring new materials, such as perovskites, that may make solar panels more efficient and cheaper to produce. Fuel cells, another energy technology, use materials that allow hydrogen and oxygen to combine chemically while generating electricity. These devices produce water as their main byproduct, making them attractive for clean energy applications. The development of these advanced materials shows how deeply modern technology depends on understanding the behavior of matter at the atomic and molecular level. Engineers no longer rely only on materials found in nature. Instead, they design materials specifically for the tasks they need to perform. From the earliest stone tools shaped by prehistoric humans to modern materials engineered at the scale of atoms, the history of materials reflects humanity's growing ability to understand and manipulate the physical world. Every new material discovery has opened new possibilities for building, traveling, communicating, and exploring. As scientists continue studying the properties of matter, the next generation of materials may enable technologies that are difficult to imagine today, from stronger structures and more efficient energy systems to medical devices that interact directly with the human body. The story of materials is therefore not only a story of the past, but also a guide to the innovations that may shape the future. As the modern world has grown more technologically advanced, another important topic has become central to the science of materials, the global supply of resources. Many of the materials used in modern technology are not evenly distributed across the Earth. Some metals and minerals are common and widely available, while others are rare and concentrated in only a few regions. This uneven distribution has shaped trade, industry, and even international politics. Throughout history, societies have often depended on access to specific materials. During the Bronze Age, for example, the production of bronze required both copper and tin. Copper could be found in many regions, but tin deposits were far less common. As a result, ancient trade networks developed to transport tin across long distances. Some historians believe that tin from regions such as Cornwall in present-day England or parts of Central Asia may have been traded across thousands of kilometers to reach bronze-producing civilizations in the Mediterranean. In the modern era, many advanced technologies rely on elements known as rare earth metals. Despite their name, rare earth elements are not always extremely scarce, but they are often difficult to extract and process economically. These elements include materials such as neodymium, lanthanum, and dysprosium. They play critical roles in modern electronics, renewable energy systems, and high-performance magnets. For example, neodymium is used to create very strong permanent magnets that are essential for electric motors, wind turbines, and many electronic devices. Without these magnets, technologies such as electric vehicles and large wind power generators would be far less efficient. Another important group of materials includes lithium, cobalt, and nickel, which are widely used in rechargeable batteries. Lithium-ion batteries power smartphones, laptops, and electric vehicles. As demand for these devices has increased, the demand for lithium has grown rapidly. Large lithium deposits are found in regions such as South America's Lithium Triangle, which includes parts of Chile, Argentina, and Bolivia. Cobalt, another battery material, has been mined extensively in the Democratic Republic of Congo, which produces a large share of the world's supply. The concentration of certain materials in specific regions means that global supply chains depend on stable access to those areas. Changes in mining production, political conditions, or environmental regulations can affect the availability of these materials worldwide. Because many advanced technologies rely on relatively small amounts of specialized elements, researchers are actively searching for alternatives and improved recycling methods. For instance, scientists are studying new battery designs that use less cobalt or replace it with other materials. Engineers are also developing ways to recover rare metals from discarded electronics through a process sometimes called urban mining. Urban mining involves extracting valuable metals from electronic waste, such as old computers, smartphones, and circuit boards. These devices often contain small amounts of gold, silver, copper, and rare earth elements. Recovering these materials can help reduce the need for new mining operations while conserving limited resources. Another area of research focuses on improving the efficiency of materials used in energy systems. For example, improving solar panel materials could allow them to capture more sunlight and convert it into electricity more efficiently. Better battery materials could allow electric vehicles to travel longer distances between charges. Stronger and lighter materials could make transportation systems more energy efficient. The challenge of managing material resources has also encouraged scientists to study the environmental impact of mining and manufacturing. Extracting raw materials from the earth can disturb ecosystems, consume large amounts of energy, and generate waste products. Modern materials science increasingly includes efforts to reduce these impacts by developing cleaner production methods and designing products that last longer. At the same time, entirely new materials continue to be discovered and developed. Some researchers are exploring materials known as metamaterials. These are structures engineered at very small scales to interact with light, sound, or electromagnetic waves in unusual ways. Certain metamaterials can bend light in ways that ordinary materials cannot, leading to experimental technologies such as improved lenses and advanced communication systems. Other research focuses on materials capable of surviving extreme conditions, such as the high temperatures inside jet engines or the intense radiation found in space. These advanced materials often involve carefully designed alloys or ceramic compounds that remain stable under conditions where ordinary materials would melt or break down. Looking back across human history, it becomes clear that materials have always shaped what societies could build, create, and achieve. Stone tools allowed early humans to hunt and prepare food more effectively. Metals allowed civilizations to build stronger tools and machines. Glass opened new windows into the microscopic and astronomical worlds. Plastics and composites made it possible to manufacture lightweight and versatile products. Semiconductor materials gave rise to computers and digital communication. Each new generation of materials has expanded the range of what humans can do. Materials science is therefore not just about objects or substances. It is about understanding the building blocks of the physical world and learning how to shape them into tools that improve human life. As scientists continue exploring the properties of atoms, molecules, and structures, the next breakthroughs in materials may enable technologies that today seem almost impossible. New materials may help produce cleaner energy, improve medical treatments, and allow exploration of environments far beyond Earth. In this way, the story of materials is both ancient and ongoing. From the first chipped stone tools made by early humans to the complex materials used in modern spacecraft and electronics, the history of materials reflects the long and continuing effort of humanity to understand and shape the matter that makes up our world.